Hello, I'm Nilam Tathawadekar, and today I'll be presenting my work on modeling flame dynamics using machine learning approaches. First, I would like to talk about my work on modeling of the nonlinear flame response of a Bunsen type flame via multi-layer perceptron. So, over the decades, the emission regulation for aircraft engines have been steadily tightened, and to meet this regulation, lean premix combustion systems are developed. But in gas turbine, this development is hindered by the risk of thermoacoustic instabilities, which causes undesired vibration that may severely damage the engine. So perturbations in incoming flow causes heat release rate oscillation, which in turn causes acoustic oscillation. And this positive feedback loop between acoustic waves and unsteady combustion gives rise to thermoacoustic oscillations. So often these thermoacoustic oscillations surface as late as engine has been built and tested. So it will be beneficial to predict these instabilities at the design phase itself. And to predict the amplitude of these acoustic oscillations, low order methods have proven to be useful if combined with the appropriate model for the nonlinear acoustic flame response. So my work focuses on using a neural network model to obtain this nonlinear flame response. A well-established strategy to model such a nonlinear flame response is by means of so-called flame describing function. So it characterizes the fluctuations of heat release rate Q dot prime produced as the flame response to the upstream velocity perturbations U prime. And it is characterized by a well-defined frequency omega and amplitude U prime. So conventionally, to obtain this FTF, the inlet velocity of the CFD simulation is excited both harmonically with both frequency and amplitude of the harmonics and are varied. And then we find an analytical fit. Although useful, this approach is restrictive as it assumes that the flame responds exclusively at the same frequency as the input signal U prime. And it neglects the possible operation of harmonics in the response Q prime. So that's why we need a methodology where the flame model can be obtained by using a single CFD simulation. So where we can use a carefully designed input excitation signal, which can be applied to CFD. So Polifsky proposed an approach where broadband excitation signal is applied to CFD and combined with system identification approach to capture the linear response. Also called as flame transfunction. But the present work uses this data collected by broadband forcing and makes use of the machine learning based approach to model the nonlinear acoustic response of the flame. On the left hand side figure, I show the experimental setup of a Cornelius flame. It's a multi-slit burner with a premixed methane air mixture with equivalence ratio of 0.8. And on the right hand side figure is a 2D CFD domain with symmetric boundary condition. So I'll be using the data created obtained using the CFD simulation. So following the work of Ian et al., we formulate a regression problem where the aim is to find a mapping F such that heat release rate fluctuation at time t depends not only on the velocity at time t, but some history of it. So this reflects the time-like nature of the system. And to solve this problem, multi-layer perceptron is used. So I would like to quickly go over the architecture of it. So this figure shows the typical representation of multi-layer perceptron. Here, TANH is used as an activation through which we model the nonlinearity of the system. Dropout is used as a regularizer. So compared to previous work of Ian Shettle, this is something different that we do with respect to our model. And also we explore deeper and wider neural network models. So mean squared error is used as a loss function to train the neural network model. For this particular data, the best performing neural network model that was found had 128 neurons in the first layer, 64 neurons in the second layer, and 32 neurons in the third layer. So let's look at how the training happens for the neural network model. So given the broadband input signal, we split it into two parts of training set and test set. Training set is further divided into validation set. Using this training and validation set data and varying the different number of hyperparameters, we train different models. The model with the lowest validation set error is taken as a best MLP model, and this is the model that we will use for further processing. And in this figure, I show the comparison of actual and predicted heat release rate by the best performing MLP model that was found on the test set data. So as we can see that it matches closely with the CFD reference. The MLP is trained, as I said before, using the broadband excitation signal. And to obtain the flame response, the best performing MLP is used to predict the flame response. So this best MLP that was found is excited with monofrequent excitation. So we vary the frequency of the excitation from 50 Hertz to 500 Hertz. And we use 3 different amplitude levels of 0.5, 1.0, and 1.5. So straight line indicates the results by neural network model, and the markers indicate the results by CFD simulation. This shaded region shows the performance by mean and standard deviation of the best 5 performing neural network models. As you can see that uncertainty around the prediction is quite low and tight bounds are achieved. And overall neural network is able to predict the gain and phase of the model of the flame quite accurately. As discussed in the introduction, the FTF neglects the excitation of higher harmonics, and the ability of neural network to do so is assessed here. So trained neural network model is excited with 3 different sinusoidal signal, each with a frequency of 100 Hertz and amplitudes of 0.05, 0.1, and 0.5. So here I show the FFT contains of the heat release rate fluctuation at the fundamental frequency and its harmonics. So at the amplitude of 0.05, the response is purely sinusoidal. But as the amplitude increases, harmonic starts to appear, and neural network is able to capture this strain. So this shows that neural network approach is capable of learning more complex interaction between harmonics than the FTF. Now we will assess whether a neural network can accurately predict the self-excited oscillations. So for this, we couple the trained neural network model with acoustic network model using flow velocity fluctuation and heat release rate fluctuations. So this represents a flame in a duct. And to study the stability of the system, length of the plenum duct is varied from 50 mm to 1000 mm. The amplitudes of the velocity fluctuations are collected, and results of the coupled neural network and acoustic network models are compared with the hybrid CFD lower order model by Yensh et al. So in their work, the flame response was obtained using CFD, whereas in our case, flame response is obtained using trained MLP model. So figure here over here shows the RMS value of the flow velocity fluctuations, and this figure shows the dominant frequency that is obtained. So after the plenum length of 160 mm, we start to observe the self-excited oscillations. And initially, second harmonic is dominant, and as the plenum length increases, fundamental frequency is dominant. So neural network is able to capture this trend. Also, it is able to capture the RMS value of the velocity fluctuations quite accurately. Here I show the time series plots for 2 different plenum lengths, so 200 mm and 500 mm. So as you can see, neural network is able to capture the dominant frequency accurately, and also the time series matches quite closely with the CFD results. So in conclusion, multi-layer perceptron with different number of hidden layers and variable neurons were explored to model the nonlinear flame response of a Bunsen type flame. The neural network model showcased the ability to learn the FTF for the lamina premix flame, and it uses only one CFD simulation for the training. Also, it is able to capture the response at the higher harmonics. And when we couple it with the acoustic network model, we are able to get the limit cycle amplitude, also shape and frequency contents compared to the hybrid CFD lower term model. So next, I would like to talk about my work on flame front prediction using convolutional neural networks for the same Cornelius flame. So given the experimental or CFD simulation data of instantaneous velocity and heat release rate, is it possible to train a neural network model to inform the flame dynamics at interpolated amplitudes and frequencies? So ability of neural network model to predict heat release rate field given the velocity field is assessed here. So for this, we use the 2D CFD simulation data of Cornelius flame that I discussed earlier. A type of convolutional neural network model called UNet is found to be suitable for this work. Heat release rate field at time t is predicted using the data of velocity field at time t and also time t minus delta t and t minus 2 delta t. So here I show the architecture of UNet. So it's a special case of an encoder-decoder architecture. In the encoding part, image size is progressively downsampled using the pooling layer. This allows the network to extract increasingly large scale and abstract information in the growing number of feature channels. And the decoding part mirrors this behavior and increases the spatial resolution with upsampling layers and reduces the number of feature layers. The skip connections concatenates all channels from the encoding branch to the decoding part. So it effectively doubles the amount of channel for each decoding block. And this skip connections help the network to consider low-level input information during the reconstruction of the solution. And each section of the network consists of a convolutional layer in addition to a nonlinear activation function called ReLU. So two cases are considered to assess the performance of the trained neural network model. So two data sets are generated for amplitude interpolation. The first with a 100 Hertz frequency and different amplitude, second with a 200 Hertz frequency and different amplitude levels. So blue data points show the training data set. The orange one shows the validation data set that is used, and the green one test data set. Similarly, for the frequency interpolation, 100 Hertz and 200 Hertz are used for the training, and inference is made at the 150 Hertz frequency. 0.1 second of simulation data is obtained at 0.2 millisecond interval. So I have 500 snapshots available for each frequency and amplitude combination during the training process. So let's have a look at the results. So here I show the performance of UNet for the test case of amplitude interpolation. Frequency of 100 Hertz and amplitude of 1.25. So on the left hand side is what the ground truth is using the CFD simulation, and on the right hand side we see the prediction by neural network model. And this figure over here shows the difference between ground truth and the neural network prediction. So as you can see for these two different shots, that a neural network is able to capture the shape of the flame quite accurately, and also the mean squared error is quite low. Here is a simple animation where it shows the performance over one period for the given particular frequency. Also here are the data, here are the results for the frequency interpolation at 150 Hertz and amplitude of 1.0. So it was observed that mean squared error is slightly higher for the frequency interpolation than the amplitude interpolation. But nonetheless, the shape obtained by neural network prediction is quite close with the CFD results. So here I have presented a study of the accuracy of deep learning for the flame front prediction for lamina case. While the results of this study are no means guaranteed to directly carry over to the other problems due to the inherent differences of solution space for different physical problems, but it serves as a good starting point with respect to general methodology, data handling, and training procedures that were used. And lastly, I would like to talk about a physics-based deep learning approach for a case study of predicting flame temperature of a 1D premix methane air mixture. So in the previous study, neural network was trained using the CFD simulation data of velocity field and heat release rate field. So main drawback of that work is that it makes instantaneous predictions of the heat release rate given the velocity fields. So how can we achieve the flame front prediction over longer horizon given the initial velocity field. So one promising approach to achieve this is integrating differentiable CFD solver with a neural network model. So in this context, Hall et al. Have presented a five-flow framework, which is a fully differentiable PDE framework that provides operators and solvers for a large class of PDEs with analytical gradients. So by fully integrating the numerical solver into the training process, neural networks can learn to reduce numerical errors of PD solvers, and it can optimally control a physical system given an initial state and a target state. So let's call this framework as a solver in the loop. So what I would like to present is a simple case study of predicting flame temperature of a 1D premix methane air flame given the equivalence ratio. So on the left hand side, we see the initial state of the temperature profile over the domain. And on the right hand side figure, we see the target state that we want to achieve. So neural network with solver in the loop is trained using data of a few equivalence ratios, and prediction is made for the interpolated equivalence ratio. So we will compare two different models. The one is baseline with just the neural network model, and then another one is where we integrate this differentiable solver with the neural network model. By integrating the neural network into a differentiable physics pipeline, the corrections can interact with the physical system after the stage and receive the gradients about the future performance of this modification. So M over here denotes the steps over which the future evolution is recursively evaluated. Solution of only neural network model diverges quite quickly after few steps. Whereas if we use the neural network and a solver in the loop approach, then we achieve the target state accurately. So this approach has a lot of potential and is an ongoing research work. Uh, Here is, in the end, I would like to show the details of my publication and secondment. So I started my industrial secondment with answers in October 2020, and I'm working on applying methods developed to model FTF of Cornelius flame to the data of inverted conical flame provided by Lewis. And also I plan to start my secondment with Min Patek in March 2021.